Chapter 4 is on chemical reactions. Formula weight is the sum of the atomic weights of all the atoms in a molecular formula. And we previously learned that atomic weight is the mass of an individual atom of a specific element. And we obtain that from our periodic table. So I have a formula here, CH4, and I want to know what the mass of my molecule of CH4 is. So the number of atoms we have of the different elements in our formula, we determine by the subscripts. So there's no subscript next to carbon, which implies there is just one atom of carbon. From my periodic table, I'm going to find carbon. Atomic number is 6, the number at the top. The atomic weight is the number at the bottom of your box. So the atomic weight, the mass of a single carbon, is 12.011 AMUs. Hydrogen, based on our formula, has 4 atoms because we have a subscript of 4 next to the hydrogen. The atomic weight of an individual hydrogen, again from our periodic table, is 1.008 AMUs. Now, to determine the mass of my formula, or my formula weight, I'm going to take the number of carbons, which is 1, multiply that by the mass of an individual carbon, which is 12.011 AMUs. And then for hydrogen, I have 4 hydrogen atoms. I'm going to multiply by the mass of the individual hydrogens, which is 1.008 AMUs. And then I'm going to add these two numbers together. So I will have 12.011 AMUs plus 4 times 1.008 gives me 4.032 AMUs. And then when I add those two numbers together, I get 16.043 AMUs. And that is the mass of one molecule of CH4. What is the formula weight of water? First, we're going to determine the number of atoms of hydrogen based on the subscript. So our formula tells us we have 2 atoms of hydrogen. The mass of one hydrogen we obtain from our periodic table, the number at the bottom, is 1.008 AMUs. The number of oxygens in my formula is no number is written next to oxygen, so that implies we have 1 atom. The atomic weight of oxygen is 15.999 AMUs. Now, to determine my formula weight, I'm going to multiply the number of atoms of hydrogen, which is 2, times 1.008 AMUs, and I'm going to add the number of oxygens, which is 1, times the mass of one oxygen, which is 15.999 AMUs. So I'm going to multiply 2 times 1.008, and that's 2.016 AMUs, plus 1 times 15.999 AMUs. Adding those two numbers together, I get 18.015 AMUs. So that is the formula weight, or the mass of one molecule of water. I want you to think of the first word that comes to your mind when I say the word mole. Some of you might think of this furry animal that digs underground. Others may think of a blemish on your face or somewhere else in your body, a mole. Or sometimes students, they think of mole, this delicious sauce used in Mexican cooking. Now, I want you to forget about the term that came to your mind when I said mole, and we're going to learn about what a mole means in chemistry. The mole is a unit to tell us the quantity of a substance. It is a definition. Just like a dozen is a unit to tell us that we have 12 of something. This is a definition. A dozen equals 12. The mole is sometimes called a chemist's dozen, and our definition is 1 mole is equal to 6.02 times 10 to the 23rd. And it could be of anything. Just like a dozen means we have 12 eggs, or a dozen can be a dozen donuts, so we have 12 donuts. A mole is 6.02 times 10 to the 23rd. And this is a large number, and we use this in chemistry as a quantity to talk about atoms, molecules, ions, etc. Amedeo Avogadro was an Italian physicist. He is the one that defined a mole. So we call it Avogadro's number in his honor, that 1 mole is equal to 6.02 times 10 to the 23rd. So this is a commonly used quantity in chemistry, so I need you to remember this definition. Avogadro's number, 1 mole is 6.02 times 10 to the 23rd. The mole is an absolutely huge number, which is very helpful in chemistry when we're measuring things that are very tiny, like atoms and molecules. Here it's written out our 6.02 times 10 to the 23rd. They do have some other numbers here instead of zeros if we were to draw this out, which you don't have to remember the ones here, but just imagine if they were all zeros. This is just to show you how large the number is. So I have written across here, this is what 1 trillion looks like. So this number is like 2 times 1 trillion when we add those two together. So it's just an absolutely large number. So just how big is a mole? Imagine if I had a mole of pennies. That would be 6.02 times 10 to the 23rd pennies. And I started stacking my pennies. And I went up with my stack of pennies up to 1 meter high. And then I continued stacking my pennies, so I actually went up 3 meters high. And then I made stacks of pennies next to the other pennies, and I kept making these stacks of pennies, and I covered the entire Earth's surface with my pennies to a depth of 300 meters. That would be 1 mole of pennies. That is a lot of pennies. Another analogy is if I had grapefruits. So if I had 6.02 times 10 to the 23rd grapefruits, a lot of grapefruits, the volume of my grapefruits would be the same as the volume of the Earth. So that's a huge number. The mole is such an important quantity in chemistry that chemists actually celebrate National Mole Day, which is on October 23rd or 10 to the 23rd, and we start celebrating at 6:02 a.m. The mole is a definition for quantity. 1 mole of an element has 6.02 times 10 to the 23rd atoms of that specific element. 1 mole of any compound contains 6.02 times 10 to the 23rd molecules of that compound. Now, sugar is a compound, and compounds are comprised of molecules. So 1 mole of sugar contains 6.02 times 10 to the 23rd molecules of sugar. If I had a mole of copper pennies, we said that that would cover our Earth's surface to a depth of 300 meters. That's something we really can't imagine. It's a huge number. But to give you an idea of how tiny atoms and molecules are, if I had a mole of copper atoms here, that is something I could actually hold in my hand. So 1 mole of copper atoms, or 6.02 times 10 to the 23rd copper atoms, is equivalent to 22 copper pennies. 1 tablespoon of water contains approximately 1 mole of water molecules. So if I had 1 mole of water, that's the same as 6.02 times 10 to the 23rd water molecules that would be contained in this tablespoon. So in chemistry, mole quantities are very useful because 6.02 times 10 to the 23rd, we said, is a very huge number, but we discussed quantities of atoms and molecules in moles makes it much more easier to deal with. Avogadro's number is a definition. It tells us 1 mole is equal to 6.02 times 10 to the 23rd anythings, whether it's atoms or molecules or anything else. We have an equality here. When we have an equality, we can put that in a fraction format and create a conversion factor. So I've created two conversion factors here. I have 6.02 times 10 to the 23rd at the top and 1 mole at the bottom. Or I can have 1 mole at the top and 6.02 times 10 to the 23rd at the bottom. So we can actually convert from moles if we have, let's say, 3 moles, and we want to convert that to how many atoms or molecules are within that 3 moles, we can use Avogadro's number as our conversion factor in either one of these formats, depending on how we would need to cancel our units. Here we have a couple of mole conversion examples. The first one says how many atoms of helium are in 1 mole of helium. So we know by definition 1 mole of helium is equal to 6.02 times 10 to the 23rd atoms of helium using Avogadro's number. So we could set up the problem to show how we could cancel units. We would start always with what we're given, which is 1 mole of helium. Then we can take Avogadro's number, which is our definition, 1 mole is equal to 6.02 times 10 to the 23rd, and set it up so our units would cancel. So we would have 1 mole of helium on the bottom and 6.02 times 10 to the 23rd atoms of helium at the top. This way our moles of helium cancel, and we just multiply 1 times this number. We get 6.02 times 10 to the 23rd atoms of helium. The next example is how many atoms of carbon are in 2.5 moles of carbon. So we're going to write our plan first, which is what we're given is moles. And we want to go from moles. What we're looking for is atoms. On our previous slide, we said we can go from moles to atoms or atoms to moles using Avogadro's number. So let's go ahead and set up our problem. We start with 2.5 moles of carbon. We're going to use Avogadro's number to convert. So we need to create our conversion factor so our units will cancel. So we have 1 mole of carbon at the bottom, which is equivalent to 6.02 times 10 to the 23rd atoms of carbon at the top. So the moles of carbon cancel, and then we just need to do the math. 2.50 times 6.02 times 10 to the 23rd gives me 1.505 times 10 to the 24th atoms of carbon. Now we do always want to remember the correct amount of significant figures in my final answer. We started with 3 sig figs. My final answer should have 3. So we need to round this number up to 1.51 times 10 to the 24th atoms of carbon. How many molecules of water are in 3 moles of water? So let's start by setting up our problem. So we'll make our plan. And we are given 3 moles of water, and we are looking for molecules. So to go from moles to molecules, we use Avo's number. So let's go ahead and solve our problem. 3.00 moles of water. We're going to use Avogadro's number as our conversion. So we want to make sure that we cancel units. So 1 mole of water is equal to 6.02 times 10 to the 23rd molecules of water. And then we can cancel moles of water, and we'll end up with an answer in molecules of water. So we just need to multiply 3 times 6.02 times 10 to the 23rd, and that will give us 1.806 times 10 to the 24th molecules. And again, we want to check our sig figs at the end. So 3.00 is 3 sig figs, which means we need to reduce our answer to 3 sig figs, and we will round our number up to 1.81 times 10 to the 24th molecules of water. The one down below says how many moles of copper are in a penny that contains 3.0 times 10 to the 22 atoms of copper. So what we're given in this case is 3.0 times 10 to the 22 copper is Cu atoms. That's my given. What I'm trying to find are moles. So whether I'm going from atoms to moles or moles to atoms or molecules, I'm using Avogadro's number as my conversion factor. So again, 1 mole is equal to 6.02 times 10 to the 23rd, and that can be atoms or molecules. So the equality is how we're setting up our conversion factors. So let's solve our problem. 3.0 times 10 to the 22 copper atoms times, we want to cancel atoms at the bottom, so we put 6.02 at the bottom in this problem, times 10 to the 23rd atoms of copper, and that's equivalent to 1 mole of copper, which is what we're looking for. So in this case, we're going to be dividing, and then our atoms of copper will cancel, and then we just divide our numbers. 3.022 divided by 6.02 times 10 to the 23rd, and that'll give us moles of copper. One thing I want to point out is when you're doing this on your calculator, I highly recommend putting parentheses around 3.0 times 10 to the 22, and then do divide, and then parentheses with 6.02 times 10 to the 23rd. Sometimes I find when students don't use the parentheses on their calculator, they're going to get their exponent off. So when I punch these numbers in using parentheses, I come up with 4.983 times 10 to the negative 2. And again, looking at sig figs, I have 3.0 given in my problem. So my final answer can only have 2 sig figs to match the piece of information I was given. So my final answer here would be 4.9 times 10 to the negative 2 moles of copper. Again, you also always want to include your units. This slide is comparing the mass of marbles to peas. If I have 1 dozen marbles, that means I have 12 marbles. If I have 1 dozen peas, I have 12 peas. So the quantities are equal for both of these, but we know the mass of a marble is much greater than peas, so the marbles are going to be heavier on our scale here. We can compare this to atoms using Avogadro's number. So if I had 1 mole of hydrogen, we know that that would be 6.02 times 10 to the 23rd atoms of hydrogen. And let's say I want to compare that to a mole of oxygen. So it's also going to contain 6.02 times 10 to the 23rd, because again, that's our definition. It's our chemist definition of a dozen, versus our regular dozen is 1 dozen is 12, 1 mole is 6.02 times 10 to the 23rd, in this case, atoms. So which one's going to be heavier? So we know an oxygen atom is much larger compared to a hydrogen atom. So they're going to have different masses. And we can compare those on our periodic table. We learned previously that the number at the bottom of your box is called your atomic weight, which is the mass of one atom in AMUs. So for example, here is 1 hydrogen atom, and we can compare that mass to 1 oxygen atom. So the mass of a hydrogen is approximately 1 AMU. The mass of an oxygen is 15.99, so it's approximately 16 AMUs. So we can compare the masses of those, and as we said, the oxygen is going to be much heavier than our hydrogen when we have equal quantities. Now what if we doubled the amount we have? So instead of one atom, we now have 2 atoms of hydrogen and we have 2 atoms of oxygen. Well, our mass is going to double, but the relationship is still going to be the same. And if we add another atom of hydrogen and another atom of oxygen, the masses will increase by 3 times the original amount for each of those, but our quantities are still equivalent. So now let's think about, instead of saying we have 3 atoms of each, what if we have 6.02 times 10 to the 23rd atoms of each? So we have equal quantities of each one, but our mass is just going to be, still about the same proportion, about 16 times higher for the oxygen than the hydrogen. So we are going to learn a new term that is called molar mass. And molar mass is also going to be defined on your periodic table as that same number. So for hydrogen, we can say its atomic weight is 1.0079, or we can say its molar mass is 1.0079. The units for molar mass are grams per 1 mole. So again, when we talked about quantity, we said 1 mole is 6.02 times 10 to the 23rd. So we're talking about mole quantities that are equal for all these elements, but where masses are going to be the same ratio. So oxygen is still going to be 16 times higher. We're just going to change the units. So 1 mole is going to be the mass in grams. Molar mass is the same number as the atomic weight of an atom or the formula weight of a molecule. The difference is in the units. So the units for molar mass are equal to grams divided by moles. So if we were looking at our periodic table and we looked at helium, we would see the mass of 1 atom of helium is 4.003 AMUs, which we find on the bottom of the box for our element helium. This number, 4.003, is going to be the same as the molar mass, so we can say this is atomic mass or atomic weight, or we could also call that molar mass, the number at the bottom. The only difference are going to be the units. So the units for molar mass for helium would be grams divided by moles. So if we look down here for helium, here's us showing the size of the atoms. Helium is one of our smaller atoms. We could fill in the chart that 1 mole of helium weighs 4.003 grams. We could also determine the number of atoms based on Avogadro's number. We know it's 6.02 times 10 to the 23rd. If we wanted to look at carbon next, 1 mole of carbon we know is 6.02 times 10 to the 23rd. Carbon atoms, Avogadro's number actually goes out more decimal places, but for this class, we only have to know 6.02 times 10 to the 23rd. We could look at our periodic table to figure out how many grams 1 mole of carbon weighs, which would be 12.011 grams, based on your periodic table. 1 mole of aluminum contains 6.02 times 10 to the 23rd atoms of aluminum. And again, based on our box for aluminum, the mass would be 26.98 grams. This slide shows us what 1 mole quantities look like for some of our elements and compounds. Now, if I wanted to react 1 mole of sulfur with 1 mole of copper to form copper sulfide in the laboratory, I could not weigh out any 1 mole quantities on my scales. My scales in the lab all have quantities in grams to measure the mass. So I can use my molar mass to determine what the grams are for 1 mole quantities. So for sulfur, I find sulfur on my periodic table. The number at the bottom is the mass for 1 mole of sulfur. So sulfur weighs 32.064 grams, and that's per 1 mole. For copper, one of our transition metals, Cu, the molar mass of copper is 63.546 grams for 1 mole. Now, if I wanted to look at some of our compounds, let's say, for example, sodium chloride, which is NaCl, and Na's molar mass is 22.990 grams per mole, and I would add that to chlorine that has a molar mass of 35.453, and when I add that together I get 58.443 grams per mole. So that would tell me the mass of the salt that's in that beaker. The one that looks like it has the biggest mass here is sucrose. Looks like the largest amount in the beaker. And for sucrose, its molecular formula is C12H22O11. So if I wanted to know the mass for 1 mole of sucrose, again, I could go to my periodic table. I would find carbon. Each carbon weighs 12.011 grams. I'd multiply that by 12 to know the mass from the carbon. My hydrogens are about 1, and I have 22 of those. And then I would add that to my oxygens, which are around 16 times 11. And my molar mass for oxygen is 342.3 grams. And again, this is all for 1 mole quantities. Molar mass is the mass of our element or compound in grams per mole. So it's the mass of 1 mole of that substance. We can use that as a conversion factor. It's already in the fraction format, so we can say we have grams per mole, or we could flip that over because they're going to be equal to each other and say 1 mole per whatever the grams is for that element or that compound. So molar mass is used as a conversion factor to go from moles to grams, or if we're given grams of a substance, we can convert to moles using molar mass. What is the mass of 2 moles of water? Let's start by creating our plan or our roadmap by writing down what we're given, which is 2.000 moles of water. What we're trying to find, our question here, is the mass in grams of water. So to go from moles to grams, or if we were given grams and we wanted to go to moles, we could go in the reverse direction. Moles to grams, we use molar mass of water. Now previous we did an example to calculate the formula of weight of water using our periodic table where we added 2 hydrogens to 1 oxygen, and we came up with a formula weight of 18.015 AMUs. And again, that's the mass of 1 molecule of water. We need the molar mass of water, which is going to be the same number, it just has different units. So molar mass of water is equal to 18.015 grams, and that's for 1 mole of H2O. So now we can go ahead and solve for our problem. We have 2.000 moles of water. We're going to use the molar mass to convert from moles to grams. We want to set up our units so the units will cancel. So 1 mole of H2O will go at the bottom, and then 18.015 grams is the mass for 1 mole of water at the top. This way we can cancel the moles of water, and then we just need to do the math, and we'll end up with grams of H2O, which is the units we're looking for. So 2 times 18.015 is 36.03 grams of water. And then we want to check our sig figs we are given 2.000. Those zeros count, so this is 4 sig figs. So the final answer should have 4 sig figs, which it does in this example. So 36.03 grams of water is the mass for 2 moles of water. How many moles of helium is 8 grams of helium? We always want to start with our plan, where we start with what's given to us. And in this problem, we're given 8.00 grams of helium. What we're looking for is moles of helium. That's our question. And to go from grams to moles, we are going to use molar mass as our conversion factor, and that's the molar mass of helium that we obtain from our periodic table. So on our periodic table, the molar mass is 4.003 grams. That's the mass of 1 mole of helium. Or we could say that's 1 mole of helium divided by 4.003 grams. We can set it up in either format as our conversion factor. We want to pick the conversion factor to cancel the units in what is given in our problem. So we're going to want to set this up so the grams will cancel. So we're going to pick the conversion factor at the bottom because that has 4.003 grams of helium per every 1 mole of helium that we'll write at the top. Now our grams of helium will cancel. Our units we'll end up with will be moles of helium, which is what we want. So then we just have to do the math. 8 divided by 4.003 is 1.9985. Then we need to look at the significant figures. We started with 8.00 that has 3 sig figs. My final answer should also have 3. So we're going to need to round this number up to 2.00 moles of helium. Using molar mass to convert from grams to moles and moles to grams is not only used in this chapter, but in our upcoming chapters throughout the semester. So it's really important to remember this. So I usually have my students stand up and we say the molar mass chant together. Grams to moles, moles to grams, use molar mass. Grams to moles, moles to grams, use molar mass. Grams to moles, moles to grams, use molar mass. Hopefully, by saying this over and over again, it will be stuck in your head and you will always remember how to convert from grams to moles or molar using molar mass, or moles to grams using molar mass. We have 101 grams of tin 2 fluoride SnF2. We want to know how many moles is this and how many molecules is this. So let's start with a plan to convert with what we're given to what we're trying to find. We are given 101 grams SnF2. We are trying to find moles. To go from grams to moles, we use molar mass. The molar mass of tin fluoride we need to calculate. We can calculate the formula weight, which will be the same as our molar mass, just the units will be different. So formula weight, as we look at our formula, SnF2. Sn, there is 1. The atomic weight of 1 Sn, or tin, is 118.7 AMUs based on the number on our periodic table. The fluorides, there are 2. So we have 2 times 19 is the atomic weight on our periodic table. 2 times 19 is 38.0. And if we add that to 118.7, we get 156.7 AMUs, the mass of 1 molecule of tin 2 fluoride. We can also say that is your molar mass, which is 156.7 grams per 1 mole of tin 2 fluoride. So now we can use our molar mass to convert are grams to moles. So again, we're going to set up our conversion factor so our units will cancel. So in this case, we want the grams of tin fluoride on the bottom of our fraction, and that is per 1 mole of tin fluoride at the top. So now we will be able to cancel our units, the grams of SN, F2, and we can multiply 101 times 1 divided by 156.7 grams. And when we do that, we come up with 0.64454 moles. And at this point, we do not need to determine the number of sig figs. We'll do that in our final answer. Actually, in this one, this is a 2-question problem, so we will record our sig figs here. So this would be 0.645 moles of SnF2. Because we have 2 questions in this problem, we want to record the correct amount of sigs for both of the questions. Now we can use the first number when we do our calculation for the second portion. So we can use the 0.64454. We can carry out more sig figs to do the calculation if that's what's left on your calculator. So the second problem is, how many molecules is this? We have now calculated moles. So our plan will be to go from moles to molecules, and to do the conversion from moles to molecules, we use Avogadro's number. Okay, so we'll set up our number of moles, 0.64454 moles of SnF2. And then our conversion factor, as Avogadro's number tells us that 1 mole contains 6.02 times 10 to the 23rd molecules of SnF2. And now we can cancel our moles of tin 2 fluoride, and we'll be left with molecules of tin 2 fluoride. So then we just multiply 0.64454 times 6.02 times 10 to the 23rd, and we come up with 3.88 times 10 to the 23rd molecules SnF2. This slide shows an overview of the conversion from grams to atoms. This can also be from grams to molecules. And in order to convert from grams of an element or grams of a compound to moles of that element or moles of a compound. So again, grams to moles, moles to grams, use molar mass of the element or the compound. And then from moles to atoms, we can convert using Avogadro's number. We can also go in the reverse direction, and number of atoms, we could also say that is number of molecules. We could go the opposite way and convert to moles of the element or compound using Avogadro's number, or moles of the element or compound to grams of the element or compound using the molar mass. How many grams is 5.02 moles of ethanol, C2H5OH? First, we start with our plan. We're given moles. We're looking for grams. To go from moles to grams or grams to moles, we use molar mass. And in this problem, I have given you the molar mass to save us time, but again, you could calculate the molar mass of C2H5OH from your periodic table by looking at the atomic weights of 2 carbons, 6 hydrogens, and 1 oxygen. If you add those all up, you would come up with 46.06 grams per mole, or AMUs. We want molar mass to do our conversion, so we're going to use units of grams per mole. So we write down what we're given, which is 5.02 moles of ethanol, C2H5OH. We're going to use our molar mass to convert. So again, we always set up the units so they'll cancel. So we want 1 mole at the bottom of the fraction and 46.06 grams at the top. So then our moles of ethanol will cancel, and then we just multiply 5.02 times 46.06, and we would come up with 231.2212 grams. And we want to always check our sig figs at the end. We were given 3 sig figs, so our final answer should have 3 sig figs. So the final answer is 231 grams of C2H5OH. How many aspirin molecules are in 0.50 grams of aspirin? Has a formula of C9H8O4. The molar mass of aspirin is given to you in this problem. So we always want to start with our plan. And with our plan, the first thing we always want to do is write down what is given to us. So in this problem, we are given 0.50 grams of aspirin, which is C9H8O4. And what we're trying to find is molecules of aspirin. So what we learned before is we can't go directly from grams to molecules. We need that intermediate step of moles. Once we have moles, then we can convert to molecules. So to convert from grams to moles, we need to use the molar mass of aspirin. And to go from moles to molecules, we'll use Avogadro's number. Now we can go ahead and solve our problem. So we're going to start with 0.50 grams C9H8O4, and then the molar mass is given. And we're going to set it up so that the grams will be at the bottom. So we have 180.08 grams of C9H8O4, and at the top, that is the mass for 1 mole of C9H8O4. So now we can cancel our grams of aspirin, and then we need to do the math. 0.50 divided by 180.08 gives me an answer of 0.0027764 moles of C9H8O4. Now we can convert our moles to molecules using Avogadro's number. So I'm going to rewrite my moles below. 0.0027764 moles C9H8O4. And then with Avogadro's number, we have 1 mole, which I'm going to write at the bottom, of C9H8O4 contains 6.02 times 10 to the 23rd molecules of our aspirin. Now we can cancel moles of aspirin and we'll be left with just molecules of aspirin. So then we do our math. 0.0027764 times 6.02 times 10 to the 23rd, and that equals 1.67147 molecules of aspirin. And then we always want to check our sig figs at the end. And so in this problem, we were given 0.50 grams, which is 2 sig figs. So my final answer needs to have 2 sig figs. So we can change this to 1.7 times 10 to the 21 molecules of C9H8O4. So we were able to convert from grams of aspirin to molecules of aspirin. How many grams are in 2.25 moles of C7H6O3, which is known as salicylic acid, which is a pain reliever? The molar mass of salicylic acid is given to you, 138.0 grams per mole. Let's start with our plan. We are given 2.25 moles C7H6O3, and what we're trying to find is grams. How we convert from moles to grams is we use the molar mass of salicylic acid. So we can solve our problem. 2.25 moles C7H6O3 times the molar mass. And again, we're going to use our molar mass as our conversion factor and set it up so the moles will cancel. So 1 mole of C7H6O3 weighs 138.0 grams. Now we can cancel the mole units, and we just multiply 2.25 times 138.0, and that gives us an answer of 311 grams C7H6O3.